Hi, this is André speaking from Western Paraná State University in Brazil. Our paper entitled "Currently Quantify a Billion Instances per Second" is a result of a cooperation between researchers from the University of São Paulo, the Western Paraná State University, and the University of New South Wales. So let's start it, defining what quantification is. For that, let's compare it with the traditional classification task as represented in this figure. Basically, getting a classifier requires a training set, a classification algorithm, and then we get our classifier. And we use that classifier to estimate the label for all instances from the test set. But what's the difference between classification and quantification? It's simple. In quantification, our objective is to estimate the prevalence of each class from the test set. Then, quantification also requires a training set, a quantification algorithm, and a test set of two or more instances. In fact, the simplest quantifier consists in classify and then count, but this strategy is considered a baseline mainly because the quantification has a main assumption that the class distribution probability between the training and the test sets are different, which is not true for classification learning. So why is quantification an interesting learning problem? To answer this question, let's consider this statement. It is not necessarily true that a good classifier is also a good quantifier, but how it's possible? Let's take a look at this figure. Here we have two classifiers, classifier H1 and classifier H2. Classifier H1 is part of the classification view and it has 0 as a false negative and 10 as a false positive. On the other hand, classifier H2 has 20 as a false negative and 20 as a false positive. In terms of classification accuracy, classifier H1 is much better than classifier H2. But in terms of quantification, classifier H2 is better than classifier H1 because the errors are balanced and most of the quantification algorithms use that information to get better quantification results like this. Then, quantification is an interesting learning problem, not only because the final goal is different, but also, and more importantly, because the learning assumptions are totally different. But is quantification a real-world problem? The answer is yes, it is. Let's consider some examples. Currently, billions of reviews are made online of many products. Knowing that distribution of customer opinion is a relevant feedback for companies to improve their products or the customer relationship. We can also use quantification to estimate the prevalence of support for different political candidates. And we can gather those information from Twitter, Facebook, Instagram, or many others social media. And we can also use that information to estimate the successful of public policies. We can also use quantification for monitoring, like counting cars for aerial image and many other applications. In fact, quantification is a very interesting task that can help us to tackle with many real-world problems. Although quantification and classification tasks have a great similarity, researchers have devoted much more effort to develop the classification task. However, in the last decade, quantification has been rediscovered by an active part of the machine learning community. Efforts have been made to formalize and to develop this task. Gonzalez and colleagues organized the first survey about quantification, and they also provide a taxonomy of quantification methods described by 3 different groups. The first one, classify, count, and correct. The second, adapting traditional classification algorithms. And the last one, distribution matching. In our experiments, we will use methods from all those taxonomy groups. Although quantification test has gained more attention from the community, most of the quantification method has focused on counting accuracy. But for a large number of applications, quantification speed is an additional criterion that must be considered. To explore the lack of contributions in terms of quantification speed, we propose the sample mean matching method, or just SMM. Our proposal is a highly accurate algorithm, and it is also orders of magnitude faster than the state-of-art algorithms. Our proposal is inspired by mixture models algorithms from the distribution matching taxonomy group. To estimate the positive class distribution, a weighted sum of the positive distribution and negative distribution estimated from the training set give us a mixture distribution. Then the weights alpha and 1 minus alpha that minimize the dissimilarity function between the mixture distribution and the unlabelled score distribution provide us the class distribution of the unlabelled test sample. In our former paper, we formalized the mixture models as a generic framework, named DICE. Thus, the following equation gives us the generic idea of DICE, where the S plus represents the positive scores, the S minus the negative scores, and S dot the testing scores. Both positive scores and negative scores are estimated from the training test using cross-validation. We also require a distance similarity, and according to the distance similarity, we can define the R variable, which is a function that converts a sample of scores into a representation that is compatible with the dissimilarity function. So, looking at this equation, we realize that it can be simplified, removing the R and DS parameters, resulting in our proposal. These modifications provide us a simplified version of the DICE equation, where R parameter was replaced for the average of scores and the DS parameter was replaced for a minus operation. As a result, we can convert this simplified equation in a closed form equation that makes our proposal simple and fast. Our experiments were divided in two different parts. In the first part, SMM is compared against the most accurate quantification methods from the same SMM family, which include H-to-Y algorithm, sort algorithm, and DICE framework. In the second part, we extend our assessment to include 15 methods for all taxonomy groups. All our analyses are conducted considering runtime analysis and counting accuracy. To evaluate the runtime answer, we simulate scores to estimate the cost for each method, varying the test set size from 10,000 to 1 billion instance with increments of 10,000. For each size variation, we run each quantifier 1,000 times under the same setup condition of software and hardware. To evaluate the counting accuracy, we use 25 binary quantification datasets. Each dataset is divided in two halves, training and test sets. Then we extract samples from the test set with different sizes, varying from 10 instances to 500 instances. In our former paper, we evaluate the relevance of test set size on the quantification assessment. Then we decide to do that. For each batch size, we vary the class distribution as well, from 0% to 100% of positive class. At the end, we repeat 10 times the whole process. Some quantification algorithms requires an extra estimation during the training phase. For instance, ACC median sweep requires to estimate the true positive and false positive rates, and we do that using tenfold cross-validation. PCC and PACC require a calibrated scores, and we do that using isotonic regression. At the end of the process, all the quantification algorithms use as a base classifier a random forest with 200 trees. We open our results section showing the critical difference diagram regarding the quantification performance in terms of mean absolute error across all 25 datasets. Remember, in our part 1, we only compared algorithms from the same mixture model family. As a result, SMM is less accurate than dice and sort, but with no statistical difference. On the other hand, SMM is much better than HDY with a statistical difference. So let's take a look at the results of the runtime analysis from part 1 of our experiments. This figure shows the samples per second according to the test sample size is growing up. Clearly, SMM is on average 3 orders of magnitude faster than dice, sort, and HDY, which is one of the main advantages of our method. So now let's look at the results for the part 2. It means including 15 different methods. These results generate a large table in terms of mean absolute error. The shadowed column represents the SMM results, and the values in bold indicate the best quantification results for each dataset. And the underlying values represent a non-statistical difference regarding the best quantifier in each dataset. From this table, we can extract some conclusion, like dice and sort have an impressive performance with no statistical difference against the best quantifier for 23 and 24 of the datasets, respectively. Our proposal also performs well, and it is outperformed with a statistical significance in only 5 of the datasets. It means SMM is fast and really accurate. This figure summarizes the last table, showing the ranking of all quantifiers for all datasets varying the test set size and the class distribution. We can easily note that DICE is the best ranking algorithm, followed by sort and our proposal. But remember that we empirically shown that there is no statistical difference between them in terms of quantification accuracy. But on the other hand, SMM is 3 orders of magnitude faster than dice and sort. This makes our proposal very competitive and the best quantifier for large datasets. Finally, this figure summarizes our achievements, relating the time complexity, which was an ignored analysis in quantification research, and counting accuracy. As a result, we show that SMM is a competitive with the state-of-the-art methods, with no statistical difference in performance, and is much more efficient than the vast majority of algorithms in terms of time complexity. As a final remarks, I would like to say that the trade-off between efficiency and efficacy is a recurrent topic in several areas of computer science, including machine learning. But until now, it was completely ignored by the quantification community. In this sense, I think our proposal brings to the light this relevant point, providing the first runtime analysis for quantification tasks and also proposing a very efficient quantifier. Actually, SMM was a great achievement, quantifying 3 orders of magnitude faster than other methods from the same family. Finally, I would like to invite you to check out our GitHub, where we include plots, codes, and our datasets. Thank you for your attention.